Hey everyone, we're going to finish off 10.1. So continuing on sequences, but finishing off that section, and we're going to talk about just a few last things here. Recursive formulas, or a recursive definition for a sequence, and then also just some information about bounding a sequence and what a monotonic sequence is. So let's talk about the recursive definition. Sequences are often defined recursively. And how you do this is it's by giving the following parts 1 and 2 here that I have listed. So by giving the value of, or let's say values, sometimes you're given more than one, of the initial term or terms. Okay, so you have to know, if you're talking about a sequence, you have to know some stuff. You have to know the first term or the first few terms or some amount of terms initially. So you have to be given that. And then you have to be given a rule. Okay, a rule, and this rule is what we call a recursive formula. Recursive formula. Okay, for calculating, and so here's how this works. You have to know some of the terms, you're given a rule to find the other terms, and so this is for calculating any later term from the terms that precede it. Okay, so if I know a couple of terms in my sequence, and then I know a rule for how to find the remaining ones, well, then I can find the whole sequence. And I know, like, the initial terms, like let's say term 1, term 2, I can find term 3, 4, and so on. That's what this is talking about. So there's a very famous sequence, and there's a lot of sequences out there. This is just one I wanted to mention because it comes up a lot in nature, actually. If you're interested, I would look into this Fibonacci sequence. And we can define it recursively. So what I have to tell you, if you don't know anything about the sequence, you have to know some initial values. So in this sequence, I have to tell you that the first term is 1, and the second term is also 1. Okay? And then I have to give you some kind of rule for how you find the rest of the sequence. So far, the sequence looks like 1, comma 1, and then there's more to it. Okay? And so here's the rule. The rule is that you find the next term, so notice how I'm writing that, a sub n plus 1. That means if I want the third term, it would be based on the previous term. Okay, so a sub n plus 1. And here's the rule. It's a sub n plus a sub n minus 1, starting at the third term. Okay, so here's what this is saying, and we'll find the next value by using this. I want the next term in the sequence, the later term, and I'm using the preceding terms to find it. So let's fill in our numbers. I'm on the third spot in my sequence. Let's just fill in the numbers here. We know that if we want the third one, okay, we know we want this to be 3. Okay, so a sub 3. So that looks like that's, well, going to be, let me switch colors. That's going to be a sub 2 plus 1. Okay. So this is letting me know that I'm basing n off of the number 2, because my next term, my third term, is the second term plus 1. Okay, so in my formula here, this is going to be a sub 2 plus a sub 2 minus 1. Okay. So this is saying the second term, let's go one more time, expand this out. The second term, a sub 2 plus, this is a 1 down here, the first term. So all this formula is saying, and I know it's, if you've never seen a recursive formula before, it might look funny, but all this is saying, and this one specifically in the Fibonacci sequence, is that the next term is the first two terms, the previous two terms added together. So I'm going to add 1 plus 1, and there's my third term. And I would do that again for the fourth term. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8, and so on and so on. And this is the Fibonacci sequence. So just to make it clear though, this is one particular sequence. They don't all have this formula. This is just for this sequence. This is its recursive formula or rule. But notice the whole point of showing you this is that you find later terms based on terms you've already seen in the sequence. Alright, the last thing to talk about here is about bounded monotonic sequences. So it's just kind of a lot of vocabulary here. It is fairly intuitive though, so I'm going to try to make it make sense to you that way instead of the whole math definition formal version of this. So convergent sequences are bounded. So convergent sequences, if they converge, then they have what's considered a bound. I do have a but over here, so but not all convergent sequence, not all, the opposite, not all bounded sequences converge. Bounded sequences, I'm just going to abbreviate, converge. So this is just a little side note, I just wanted to just throw that in there because sometimes you might have bounds for your sequence, but your sequence might like bounce back and forth within those bounds, so it might not converge. So here's this idea. I have this example here. The sequence 1/2, 2/3, 3/4, which each term is found by taking your n value, which term you're at, and dividing it by the next number above it. So if you think about what happened next in this sequence, I'm on my 4th term here, so let's just make a space and fill this in. My 4th term would be 4 for n, and then 4 plus 1, or 5 on bottom. Okay, so I graphed some of those points of our sequence, and so look what happens. The first term is 1/2, the next is a little bigger, 2/3, the next is a little bigger, 3/4, and so on. But if you think about this, even if I go really high on this list, like let's go higher, let's pick 100, 100 over 101. Okay, let's go even higher, 1,000, but then the bottom would be 1,001. Okay, and so if you realize what's happening here, you always have less on top than you do on bottom, so it's always a fractional amount, and it would always be less than 1. Okay, so what we say here is that 1 is an upper bound for our function. So upper bound, or bounded from above, our sequence, excuse me, is bounded from above. So upper bound, or you could say bounded from above. And then let's see, this one's interesting because there is also a lower bound. Okay, this sequence, if it's going to keep going up like this, well, it's never going to go lower than 1/2. It actually equals 1/2 right here. So maybe right underneath 1/2, it's never going to go any lower than that. So we have a lower bound for our sequence. Okay, or our sequence is bounded from below. So just think of this like a ceiling and a roof, or sorry, that's the same thing. A ceiling and a floor for a room that you're in. Officially you shouldn't be able to like go through the floor or jump through the ceiling, and so those are the bounds for the room. This is the same thing for our sequence: upper bound, lower bound. Now there is something a little bit more detailed that I want to mention. You have lots of lower bounds and lots of upper bounds, so you want to be a little bit more specific here. I could say that this is also an upper bound. Let's move up. Let's say 1.5. This is also an upper bound. It's higher than my sequence. Nothing in my sequence goes that high. This is also a bound. Okay, it's also above. It's like another ceiling above the room. This is also an upper bound, and so on. And so when you want to get specific about, well, what is the real upper bound that's closest to like boxing in my sequence, we call that the least upper bound. Okay, because it's the smallest of all of these like ceilings to our sequence, so the least upper bound. And then the same thing but the opposite direction. This, if I say how about 1/4, That's bounding from below. That's still bounding my sequence. There's nothing in my sequence lower than that. Same thing down here. 0 is also bounding the sequence from below. There's nothing on my sequence lower than that. But I want the closest one to boxing in my sequence, so we call this the greatest lower bound. Okay, because it's the highest one of all of the lower bounds, closest to my sequence, like boxing it in. So this one had both a upper bound and a lower bound. It was bounded from above and below. And so when that happens, we say that the sequence is bounded. So a bounded sequence, I know it sounds like I'm just saying the same words over and over again, but a bounded sequence, it's more specific than just having boundaries. It's bounded from below, above and below. So is bounded from above and below, both. Because sometimes some sequences you don't have both. Okay, so if you want to say the sequence is bounded, then that means mathematically that it has both boundaries, a top and a bottom boundary. Because sometimes there might be a bottom boundary, but then your function just keeps going up, and that wouldn't be considered bounded. Now the last part here is about monotonic. Okay, what does that mean? So this sequence is actually an example of a monotonic sequence, and here's why. So monotonic is just a word for saying that the sequence kind of does one thing. It doesn't go up and down. And so monotonic is a sequence that's either non-decreasing or exactly the opposite, non-increasing. Okay, so this sequence is monotonic because it is non-decreasing. I know you might just say, why don't I just call it increasing? Because there's a subtle difference. It's non-decreasing, meaning that yes, this one in fact actually increases, but also what would be considered non-decreasing is if it just stays the same. So a constant sequence would also be considered monotonic because it would just stay the same. It wouldn't decrease, non-decreasing, but it also wouldn't increase. So it would actually satisfy both of those. So if a function either just only goes up, or only goes down, or just stays the same, that's when it's called monotonic. Alright, so why we care about monotonic sequences is mostly because of this theorem right here. That is very useful to know if it's monotonic. If a sequence is both bounded and monotonic, then we know just by those two facts that it will actually converge. So if you know that your sequence is bounded, meaning from above and below, and it's also either only going up, only going down, or staying the same, that's what monotonic is, then we know that the sequence is going to converge. So let me just show you a couple of images. In this one here, this sequence is bounded, but this one does not converge, and it's because it's not monotonic. So it's bounded below, we say by lowercase m. It's bounded above by this capital M, but the points or the values of this sequence, they're not converging to any specific value or limit value. So even though this sequence, the blue dots is bounded, it is not monotonic, therefore it does not converge. But this sequence does. So this is very similar to the example we just went over. We have a sequence that's bounded. Notice it's bounded above by this limit L, or actually capital M is technically a boundary, but that might be like just a regular upper bound, not the least upper bound. I would say like L is the least upper bound. It's also bounded below. If you were to draw a line, let me see if I can draw a line really quick. Bounded below right about here. Sorry for my squiggly line, pretended straight. So it is bounded. It's bounded from above and below, and then it's monotonic. In this case, it's only going up. It's increasing. And so because all of that is true, notice that it does actually converge. It converges to whatever number L is. All right, that's it.